Hello everyone. In this video we'll be discussing polynomial fitting, which is actually a very interesting idea, and it has to do with finding the closed form for a given sequence. It only works sometimes, but it's a quick check to see when it does work, and then from there you can apply the technique to actually find the closed form. So I'm first going to start off with this example. I was going to start off with actually naming what certain terms are, but then I started to realize it becomes a little tedious, and it's actually best to just see an example and point out what these things are called. So the first thing I'm going to do is discuss this so-called successive difference. And a successive difference is when you take the difference between consecutive terms in a sequence. So we're not given the 1 beyond 20, so we can't take the difference between those two, but we can still see what the first successive difference is. So it's the sequence that are terms that result from the differences here. So 6 minus 0 is 6, 24 minus 6 is 18, 60 minus 24 is then, what's that? That's going to be 36. And then this minus that, that's 60, and so on. Now already we kind of see a pattern. So that kind of helps maybe. You see the first successive difference and you see some pattern possibly. Now as it turns out, looking at that pattern, it's actually very difficult to use information in that to go back. So for example, I can see this is 2 times 3, or maybe better to look at multiples of 6. So 6 times 1, 6 times 3, 6 times 6, 6 times 10. And then you can look at the pattern there between 1, 3, 6, and 10, and so on. But even if you have that recognition, it's actually very difficult to find the original closed form based on this one. So we're not quite doing that, but still, what we're going to do is we're going to actually keep taking successive differences until we notice that the pattern is super obvious. So here, like I said, there may be a pattern that you can notice right away, but let's just keep going. So now, the successive difference here, which is called the second successive difference, will be 12. Difference between those two are 24. And the difference between these two are, actually this is 24. This is not 24, this is 18, my mistake. There we go. Now notice, however many terms you have, you'll always have one last term when taking the differences because of the way the counting works out. Let's do one more, and you'll see the difference between these ends up being 6 all the way through. So again, this is called the first successive difference. Difference, there we go. This is then the second successive difference. Let's write that for short for successive difference. And this is then the third successive difference. Now, what you notice about the last one we saw here is that if you take the next successive difference, you'll get 0, assuming these are all 6, right? And it looks like we only have 2 6s, but as it turns out, the pattern I have in mind here will amount to all 6s in the third successive difference. So that means the next successive difference, the fourth one, would be all 0s. So the one before all 0s is all 1 number, so it's constant. So because this is a 3 here, we call this sequence delta 3 constant. So delta k constant just means that your k successive difference is a sequence of just one constant number. And what that number is not super important. I'll actually explain what it is in a little bit, but it doesn't matter actually what the number is, just as long as we know it's constant. In fact, whatever successive difference you're at, in this case 3, tells you the degree of the closed form as a polynomial. So it tells you kind of two things. It tells you that its closed form is a polynomial, and it also tells you its degree. So here's this theorem that says a sequence is delta k constant if and only if its closed form is a degree k polynomial. So here, based on this theorem, if we assume this to be true, then since this is delta 3 constant, then that means that this closed form of this, whatever this general term is of the sequence, will be a degree 3 polynomial. Okay, we'll actually take a look at that specifically in the next screen. I'll show you the technique. But for right now, let's kind of notice something here. So here I have powers. I have 1, 2, 3, all to the 1, all to the 2, and all to the 3. So in fact, really, these general terms are n to the 1, n to the second, and n to the third are these general terms, these so-called closed forms. Okay? that's squared. Now if you take the differences of these, your successive difference is just 1s. And in fact, this is delta 1 constant. Notice the relationship between the first successive difference and n to the 1. The degree is 1. The successive difference here, well, let's see, this is 1, 4, 9. Let me write it down actually. 1, 4, 9, 16. Maybe that's better. Taking the difference here, we get 3, and 5, and then 7. And as it turns out, the next ones are 9, 11, 13, and so on. So they're the odd numbers. Taking the difference here, for the second successive difference, we get all 2s. So notice the constant sequence here is the second one, so we say that this is delta squared constant, delta 2 constant. So that means that the degree of its polynomial closed form is 2, like we clearly see here. And for this one I think it gets pretty interesting. So this is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is then 125. Now taking these successive differences, let's see what we get. 8 minus 1 is 7, 27 minus 8 is 19, 64 minus 27 is 37, and 125 minus 64 is 61. Okay, taking the second successive difference, we get 12, 18, 24. Taking the next successive difference, we get all 6s. Much like we got for this first example, actually. So notice the third successive difference is all constant, so we call this sequence delta cubed constant, or delta 3 constant. And notice the closed form n cubed is a polynomial of degree 3. Fantastic. Now, what I want to notice is something a little maybe more deep, and it's actually a pretty interesting connection to what these numbers actually are. These are all 1s, these are all 2s, these are all 6s. And if you were to do the same thing for fourth powers, the fourth successive difference will all be 24. And as it turns out, if you have a polynomial of degree k, the kth successive difference will always be k factorial, believe it or not. So that's interesting to see. And what's really interesting, I think, is if you look at the 0 powers, they're all 1s. And what's the 0th successive difference? It's just the sequence itself, which is all 1s. So that kind of gives you a hunch that, 0 factorial should be defined to be 1, based on this idea. So it's nice to see maybe that kind of tying in to factorial a little bit. That's all I'm going to say here. I'm going to erase the board and now move on to the next idea, which is just the actual technique in finding the closed form. So now that we understand that this theorem is true, or at least we have a hunch that this is true based on these 3 examples below, we can now apply it to, let's say, something like this and actually find the closed form. So let's take a look at that right now. Okay, so now back to this problem. I've erased everything else. We know that now this is delta cubed constant. So that means that its closed form is it's a degree 3 polynomial. So what I'm going to do is I'm going to say a sub n is equal to, maybe a sub n is kind of, I guess it's okay. I'm going to do this. I'm going to call it an cubed plus bn squared plus cn plus d. So a sub n for me sounds kind of strange, but here it's because I'm using a again. But here a represents a number where a sub n represents these terms, a1, a2, a3, and so on. So notice this a has no subscript, so it's a constant. Anyways, let's take a look. So how do we find out what each of these things are? So this is a general cubic polynomial in the variable n. Now, if I label this as a0, a1, a2, a3, and a4, so that's telling me that we're starting with 0, then when n is equal to 0, a0 is just d. And since a0 is equal to 0, that means d must be 0. So we know that much. The next thing we're going to do is just plug in all the other values we know. So a1 is, well, replace all of these n's with 1s. You get a plus b plus c plus d, and that's because anything to, 1 to any power is 1. Also d is 0, so that goes away. And a1 is 6, so we get this equation. A plus b plus c is equal to 6. Basically, we'll develop this kind of system of equations. We're almost there. It's quite a bit of work, actually. But let's see. When n is equal to 0, 1, and now finally when n is equal to 2, maybe not finally, but almost. When n is equal to 2, we get a2 is equal to, replace all these n's with 2's. We get 2 cubed is 8a, 2 squared is 4 times b, and 2 times c. And again, a2 is 24 here. So we get 24 is equal to 8a plus 4b plus 2c. This equation can be simplified by dividing through by 2. So we get 12 is equal to 4a plus 2b plus c. Okay. What about when n is equal to 3? So actually, we could jump to 4 if we wanted to, but I'm just going to use 3 here. When n is equal to 3, we have a sub 3 is equal to 3 to the third is 27. 3 to the second is 9. And 3 times c is just 3c. Perfect. And now that's 60. So 60 is equal to this. Divide by 3 to clean this up. You get 20 is equal to 9 plus 3b plus c. So now I'm going to, I guess, clean up some of this and write the system of equations that contain these 3 useful formulas we found. We also know d is 0. So I'm going to erase this and write that system of equations now. All right, so far we have found out that this is a cubic polynomial, and we got the system of equations, and we also found out that d is equal to 0. So in fact, I'll just kind of wipe that away. D is 0, that's gone. Okay. But now what about, how do we solve the system of equations? Well, I'm just going to use some kind of elimination here. So if I just subtract these two, for example, let's just do bottom minus top. So we get 3a plus b, the c's cancel out, and we get equals 6. That's 12 minus 6 is 6. Okay? And actually, similarly, if we subtract these two, the c's also cancel. 9 minus 4 is 5, doing again bottom minus top. 3 minus 2 is 1, and then 12 minus, 20 minus 12 is 8. And now we can actually subtract these bottom minus top again. The b's cancel out coincidentally. So we get 5 minus 3 is 2a, the b's cancel. 8 minus 6 is 1. Not 1, but 2. Then dividing by 2 here, we get a is equal to 1. All right, so we know a is 1. So I'll replace this with a 1. And we can plug that back in and see what we have now. So if a is equal to 1, we have 1 plus b plus c is equal to 6. 4 plus 2b plus c is equal to 12. And you know what? That's, I guess, all we really need. Well, actually, what I was going to say is you can actually plug 1 back in here. Maybe that's better. We don't actually need to plug it back into all of these. We could do that, actually, but let's first... I'm going to still plug it into the first one, but let's first actually plug it into one of these. So plugging this back into, let's say, the top one, we get 3 times 1 is 3, plus b is equal to 6. Subtract 3, b is equal to 3. Okay, plugging that into this guy now, we get 1 plus 3 plus c is equal to 6. So that means this 1 plus 3 plus c is 6. So that's 4 altogether. So subtracting 4 from both sides, we get c is then 2. Perfect. So now plugging these in, we already plugged in a, b is 3, c is 2, and there we go. Now, I was actually kind of getting stumped on this because the way I got this sequence was with a different closed form. And the reason why that happened, though, is because the closed form I used was starting at 1, not starting at 0. Now, there's kind of this interesting thing we can do to kind of shift that. I am going to notice that actually this factors. If you pull an n out, you get n squared plus 3n plus 2. And that factors further as n plus 1 times n plus 2. So I'm going to actually erase this to show that just real quick here. n plus 1 times n plus 2. Great. So what was what did I use instead of this? I didn't use this. I mean, I guess we can maybe look at this right now and see that this is indeed correct. So like, for example, when n is 0, that's 0. When n is 1, that's 1 times 2 times 3, that's 6. When n is equal to 2, that's 2 times 3 times 4. 2 times 3 is 6, times 4 is 24. When n is equal to 3, 3 times 4 times, that's 3 plus 2 is 5. 3 times 4 is 12. 12 times 5 is 60. So that definitely works. But actually what I used was this closed form instead. So how is this the same as this? Well, first off, I started with 1, not with 0. So is there a way to connect these if we start with 1 instead of 0? I mean, obviously it's a kind of a tangent a little bit, because you can start with whatever you want as long as, it's within the context of the problem. I mean, if I see you label it A0 and so on, then I'll know that that's what you use. But if you started with 1, then it's different. Now, I wanted to start with 0 so that we can get rid of D right away. Otherwise, if we were to start with 1, then it's more complicated and takes longer to find these things. But it would actually be less work because there's only 2 terms surviving here. But still, how do we connect these? Well, what I'm going to notice is that if we were to re-index this, where I want this to be with 1, that 2, that 3, and that 4. So I would call this, I guess, a sub n plus 1. Let me see if that works out. So if a sub n plus 1, when you plug in 0, it doesn't quite work. Because I want to plug in 1 here. If you plug in 1 here, then a sub 1 is 1 cubed minus 1, that's 0. But if you plug in 0 into this, you get a sub 1, which is this when you plug in, you're not plugging 0 in here, you're getting a sub 1 this way. So when you plug 1 into that, you get 6. So these are obviously different. But how do we relate these, I guess is what I'm trying to kind of get at. How can we re-index this? I don't know if that's actually possible at this point. I mean, it probably is. What a part of me kind of wants to say is you could just replace n's with n minus 1s. But if you were to do that, then you get n minus 1, n minus 1 plus 1 is n, and n minus 1, oh, that actually works, because n minus 1 plus 2 is n plus 1. So this is n times n minus 1 times n plus 1, but of course n minus 1 times n plus 1 is a difference of squares, which is n squared minus 1, and then distributing, you get n cubed minus n indeed. Now why this works is because replacing n with n minus 1 means instead of starting at 0, you would start at 1. So your n minus 1, when n is 1, would be a0. So this a0. So you kind of have to relabel them, I guess. So they call this b sub n, where b sub n is the sequence starting at 1, and a sub n is a sequence starting at 0. These are the same when you have a sub n minus 1. So we're changing this to start at 1 instead of 0 by changing the subscript. Replacing n with n minus 1, so that 1 minus 1 will correspond to 0. Sounds funny. But again, all we're doing is replacing n with n minus 1, and we get that. So sorry for the digression. I just wanted to explain where my mind was as far as what I started with versus what we got for the answer, because it was kind of a little confusing for me in the back end of things. But this is the result. This is the closed form for this if you start at 0. If you were to start at 1, then you would get that. So let me just put for n being a natural number, and here for n being a natural number with 0. So you get different things. It'd be interesting if you want to try this to figure out what it would be, or like how the work would go doing it that way. But I think in general, it's best to actually start with 0 because you can get rid of your content term right away. Maybe not get rid of it, but find it a lot quicker anyways. So I want to do one last example. I'm going to erase the board. I'm going to word it more kind of like a word problem, but it's going to be just as fun as what we just did. So let's take a look at that right now. Right, so like I mentioned, this is worded more like a word problem, but it's actually a very similar problem to what we just saw. So it says, find a closed formula for the number of squares on an n by n chessboard. So a chessboard is the same as like a checkerboard or checkerboard pattern kind of thing. Now, at first glance, you may think, well, it's just n. So like, for example, if you had, just to kind of start small, let's say we have a 3 by 3 chessboard. So n is equal to 3. And you may think, okay, it's pretty obvious. There's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 squares, right? Well, actually, if you think a little more about it, there's actually more than that. So how are there more than that? Well, you can look at the 2 by 2 squares that are here. So how many 2 by 2 squares are there? Well, here's 1, here's 2, here's 3, here's 4, and we also have this big one. So if you kind of count here, when n is equal to 3, the number that we have is, well, it's going to be 9 plus the 4 2 by 2s plus the 1 big one. What about when n is equal to 3? Oh, sorry, n is equal to 4. We did n equals 3 already. When n is equal to 4, well, you just kind of extend this. Like that. So you still have the amount we had here, but then you have more. How many more? Well, I mean, I guess one can say that this pattern is kind of repeated 4 times, but I don't know if that's the best approach. Maybe the better approach would be to kind of start from scratch here and just think in the same way we thought of the 3 by 3 case. So in the 3 by 3 case, we started looking at the little squares, then we looked at the 2 by 2s, and then we saw the big 3 by 3. So we're going to increase dimension basically. So let's first look at the 1 by 1s, and there's of course 4 by 4 of them, so there's 16 of those. Okay, that's pretty obvious. And now what about the 2 by 2s? So they overlap, but there's 1 here, okay, 1 here, 1 here. So there's 3 there. And then we have a 4th one, 5th one, 6, 7, 8, 9. Now, a nicer, obvious way to kind of see this is that all I'm really doing is drawing a square around each of these center points. And of course, there are clearly 9 of those center points. See that? I don't know how well the red is coming out of the camera, but I'm trying to draw a red dot on each of those center of those 2 by 2 squares. There's 9 centers, so there's 9 squares. Okay, great. And now what about the 3 by 3s? Well, the 3 by 3s, you can see that as the same kind of center idea, only now the center is going to be this actual block will be the center of this 3 by 3 square. See that? So then for the next overlapping one, it'll be this one, then this one, and then this one. So there's clearly 4 there. And then finally, after 3 by 3 is 4 by 4, and there's 1 of those. So if you don't see the pattern already, it's just the sum of squares. And if you wanted to verify for n equals 2, it's just this, and for n equals 1, it's just that. There's only 1 by 1, and there's 5 squares in a 2 by 2, as it turns out. And again, I'll let you verify that on your own. You can kind of keep going just to see if that is indeed the case. But it seems like when we have n is equal to n, just generalization n, it's 1 plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. Notice 4 squared 16, 9 squared is, or 3 squared is 9, and 2 squared is 4. So it's a pretty kind of obvious pattern once we keep doing it a bunch of times. And we also have this sigma notation, k equals 1 to, I guess, n of k squared. Okay, and I guess technically if you want to talk about a 0 by 0 chessboard, then there would be 0 squares there. So that's something we can possibly consider as well. So now I'm going to erase the board and write this a little more formally, but I'll just do it right here, it's fine. So we know what the formula looks like now, but now can we write out based on the formula? So let's call this a sub n is our sequence, and it's this. It's the sum from k equals 1 to n of n squared. Or k squared, sorry. Because we're stopping at n, right? So I guess we can start at 0 just so we include a 0th term. So for the 0 by 0 chessboard, it's 0, then 1, and then when you stop at 2, that's 1 squared plus 2 squared, that's 5. And then 1 squared plus 2 squared plus 3 squared, that's 1 plus 4 plus 9. So it's this plus 3 squared, that's going to be that plus 9, that's 14. So then we're at 4. This plus 4 squared is 16, so that plus 16 is 30. And then we have 5 squared, so let me just count 0, 1, 2, 3, 4, 5. 5 squared is 25, added to this is 55. And it goes on and on and on like that. Okay, so now what are we going to do to actually find this, the closed form of this? Well, what I'm going to do is I'm going to find the successive differences and see if we ever do get a constant. So the first successive difference is going to be the sequence 1, 4, 9, okay, 16. So we just get the squares, all right? That's pretty obvious. But this actually gives me a lot of hope because notice the sequence of squares is a degree 2 polynomial. So I know right away this is delta squared constant. So that means this must be delta cubed constant right away. But just to show it, let's keep going. We already did this earlier, actually. We got 3, 5, 7, 9, right? As a sequence, the successive difference of this are all 2s, because remember that's 2 factorial. So that's kind of interesting because I mentioned earlier that that wouldn't be the case, kind of, right? I mentioned that if you have a degree 3 polynomial, then it should always end at 3 factorial, which actually doesn't quite seem to be the case here. So maybe I misspoke actually when I said that. But it's still an interesting thought. And you can kind of compare when you actually have a repeated sequence and actually compare that number to the degree and kind of see what happens. Maybe it has something to do with the leading coefficient, perhaps. That's an interesting thought, but it's an idea to play around with. It's more of a digression than anything, but it's still an idea. But we don't care about that. We care about the successive difference until we get all constant terms. So that's the first, second, third. So this is delta cubed constant. So what does that tell us? That tells us from our theorem that a sub n is cubic. So I'll write it as an cubed plus bn squared plus cn plus d. When n is equal to 0, a sub 0 is 0 itself, so I'll write that here. That's a0, a1, a2, a3, and a4, and a5. We don't need that many of them, but that's okay. So a0 is 0, we know that. When n is 0, you just get d, so d is 0. So count that out. Great. What about when n is 1? When n is 1, a1 is 1, and then you just get the sum of a plus b plus c. When n is 2, you get 5, and 2 cubed is 8, 2 squared is 4, and then plus 2c. And then finally, for when n is equal to 3, a3 is equal to 14, and 3 cubed is 27, 3 squared is 9, and then we have 3c. So now we have a system of equations, so I'll erase the board now, and then we'll continue with that process. Right, so here's where we are so far. We looked at this question and then we ran some experiments, kind of figuring out what we're being asked to find. We found that the general term of the sequence should be the sum of squares, partial sums of squares. And then using successive difference ideas, we found out that this is a cubic with a constant term of 0. And that led to this system of equations though. So now I'm going to solve this by multiplying the top by 2 and subtracting. So what do we get there? I'm just going to do bottom minus top, so it's going to be 8 minus 2, that's 6. Okay, 4 minus 2, that's going to be, again, we're distributing that, so it's all 2, so 2a, 2b, 2c is equal to 2. So 8a minus 2a is 6a, 4b minus 2b is going to be 2b, and then 2c minus 2c cancels, and you just get 5 minus 2, which is 3. Good. And now for the next equation, I want to eliminate c again a different way. So now instead of multiplying by 2, I'm going to multiply by 3 so that we actually get cancellation with the third equation. So distributing that, we get 27a minus 3a, that's 24a. And 9a minus 3b, that's going to, or 9b minus 3b, yeah, that's going to be 6b. And then 14 minus 3 is then 11. Okay, so what can we do here? Well, we can multiply this by 3 and then subtract. So notice if we distribute this, you get 18a plus 6b is equal to 9 after distributing that. Okay, then subtracting, again, just doing top minus bottom, we get 6a, the b's cancel, and 11 minus 9 is 2. So that means a is equal to 2/6 or 1/3. Perfect. So great, we know a is 1/3. Fantastic. What about b? Well, we can plug it back into, let's say, the original first equation here. Not this one, but this one. So we have 6a times 1/3, that's just 2, plus 2b is equal to 3. Subtract, you get 2b is equal to 1. Divide by 2, b is equal to 1/2. Okay, so we're getting fractions, funny enough. In fact, remember what I said, that if you have any cubic polynomial as your closed form, and you take its successive difference, you would get 3 factorial. And I kind of made that claim. Since the leading coefficient here is 1/3, notice 1/3 times 6 factorial, or 3 factorial, which is 6. 1/3 times 6 is 2. And we saw the third successive difference of this polynomial was 2, not 6. So there probably is a link between the leading coefficient and the degree. But anyways, again, I digress. Let's find c now. Plugging them into this. A is 1/3, b is 1/2, plus c is equal to 1. Now, if you combine these, multiplying this by 2 and multiplying this by 3, this is 5/6. Right? That's 2/6 plus 3/6. So that's 5/6. So 5/6 plus 1/6 is 1, so that means c must be 1/6. Great. So c is 1/6. But now, the last thing I'm going to do, we're done basically. The last thing I want to do is I want to erase all this scratch work in finding those coefficients, what we'll do right now. And we'll actually try to make some sense of this, because why this doesn't make sense to me right now is we have fraction coefficients here, but all the terms ended up being, integers, not fractions. So I'm going to find a common denominator here, multiply this top and bottom by 2, this top and bottom by 3, so we have a common denominator of 6. And on the top we have 2n cubed plus 3n squared plus n. Notice we can factor an n out from the top. So we get 2n plus, well, 2n squared plus 3n plus 1. Is that right? All over 6. So it seems right. Now that actually factors, believe it or not. How does it factor? I believe it's 2n plus 1 times n plus 1. So you can kind of check that. 2n times 2n is 2n squared, 2n times 1 is 2n, 1 times n is 1n, 1n plus 2n is 3n, and then 1 times 1 is 1. So that checks out. And I meant to write over 6, sorry. Now, how we know this is always an integer? Well, 2n plus 1 is always going to be an odd number because it's an even number plus 1 is odd. And then n is either even or odd, so n plus 1 is also going to be even or odd. Kind of like the opposite parity. So if n is odd, then n plus 1 is even. And then we have an integer that's always odd. Kind of want to say one of these is always going to be a multiple of 2, and one of these will also be a multiple of 3, so that the whole numerator is a multiple of 6, which cancels this out, suggesting that this is indeed always an integer. So that's kind of a consequence, but that's not really what we care about. What we actually care about is finding our closed form, which we have. So there it is. Well, we know it's an integer based on how we got to this. We kind of started with a sequence of integers, which were sums of squares. So a nice consequence of this problem is that the sum of squares, the partial sum of squares from 0 to n, is n times 2n plus 1 times n plus 1 all over 6. So that's kind of interesting consequence here. And we'll talk more about this in, actually in, not, I think, I'm trying to think if it's the next, I don't think it's quite the next video, but the video after this will kind of be looking at equations like this, and we'll actually be able to prove them with a very specific technique. It's called induction. It's pretty magical, actually. But we still have another thing to discuss before there.
We still have a lot to discuss, actually. It's going to be quite a lot of fun. Hope to see you all there. Hope you enjoyed this. Thank you all for watching, and I'll see you.